Okay, actually, my part have already finished for the chi already, because I have shown you how to derive the chi1 and chi3. Maybe some discrepancies of the constant, but that one is never mind. You just follow the paper's constant. I don't really sometimes I make a little bit changes of the constant. I think should be alright. If the concept is delivered, then should be okay lah. Alright. So, and last week I do mention about, okay, last time, I mean, our last meeting, I do mention about the derivation of the wave equation. And then maybe next week, I try to make something that equation that can get the bistability, you see. So I think your project, I try to make it as simple as possible because I think I did aware that the scope of the study is beyond yours because it's enter into the non-linear region. All right, but anyway, we try to make it. We try to make it. So let me share the file. Wait for a moment. I want to open the textbook first. Let me see. Okay, share. Okay, so remember last time I mentioned about we have to use the textbook, the Griffey. So can you see the screen? So this is the Griffey, chapter 7. All right. Can you see my screen? All right. So you can see that we have to basically use the Maxwell equations in matter. Okay. I highlight here Maxwell equation in matter. So we use several of it, and I do copy paste here. So in matter, the textbook is in general. So you can see that I use the red line to cross the term. So no m is 0. No rho f, so this term is 0. No jf, so this jf is 0. So we consider simple dielectric medium. So, okay, based on this, actually you're going to study this next semester. So you see the problem is the next semester, then only you study the derivation of wave equation. But anyway, today I will show quickly to you. Okay, so if you want to get the wave equation from the Maxwell equation together with the constitutive relation, okay, there are two here, P and D. Okay, so what you need to do, okay, okay, what you need to do is we start from this, okay, curl E. So we start from this. I hope that you can see my cursor. We start from this. Okay, and then we take the curl of the whole equation. Means that we take the curl on the left hand side and also on the right hand side of the equation. So the operator curl and the del over del t, you can interchange the sequence of operation because we consider B a nice function. I mean continuous function, derivable function. So you can always exchange the operation because the curl here should be after the del over del t, but we just change the sequence so that the del over del t outside the bracket. The bracket, we always do the bracket first. So by using the vector identity, curl, you have these two terms. I think you have done in your vectors. And then this one, we are going to use term to simplify it. Okay, so here we have two terms. So the divergence of E, we can always refer to the other Maxwell equation. From the constitutive relation, rho f0, D equals to epsilon E. So you substitute the D equals to epsilon E. Epsilon just a constant. So divergence of E equals to 0. So from this equation, your divergence of E equals to 0. So you have this. So you have this. And then from the other Maxwell equation, just now we have curl B. So curl B, we have to look at this curl H. H relate to B like this. So if you rearrange this equation, your B equals to mu naught H. B equals to mu naught H. So curl B equals to mu naught curl H. Right? So B equals to mu naught H. So curl B equals to mu naught curl H. So we can substitute these results here. We can substitute these results here. Okay, then the new equation I use arrow. So so you have the 0 here. This you have the mu naught outside, inside become curl H. Okay, and then curl H, we use another Maxwell equation. So you have to use almost all the Maxwell equation. Curl H, what is your curl H? Curl H is equal to this. Because of JF equals 0, curl H equals to del D over del T. So curl H equals to del D over del T. Okay, curl H equals to this. So we substitute this into this bracket. So the del or del T outside, so you have this. So this is curl H. So at the end, you have this this divergence of itself operate on E. And okay, I have to cancel the negative. Both sides negatively become positive. Then you get this equation. So you see the left hand side E, left hand side is D, is not balanced. We have to use constitutive relation. Just now the constitutive relation is what? Is this? Is this? D equals to epsilon naught, epsilon E. Okay. And if you refer to textbook, you know that epsilon E equals to epsilon naught E plus P. Okay. D equals to this. Epsilon naught E plus P. Okay. So you substitute inside D into this position, right? So before you do anything, you collect the del over del T. So you have the del square over del T square, and then the D here. Then you do the time derivative, double time derivative. So the first term will give you mu naught epsilon naught del square E over del T square, and then plus mu naught del square P over del T square. So you get this equation. So later on, you know that this P will relate to E, right? Okay. Can you follow? Okay, so this is another step results. Let me drink some water. Let's see. All right. So when we achieve this, you know that I think you have gone through your 219. Let's see the mathematical methods. You know that this equation you can solve by separation of variables, right? You know that E is function of time and also Z, right? Okay. So that's why you can see this part we have no problem because this part is homogeneous equation. But we have this part, this P here. So that's why from the beginning, from the starting direction, we have to find the P. Now you can see what is the importance of P. This P will determine the linear and nonlinear properties, whatever the properties are determined by this P. All right. So I just copy paste from what we have done in the beginning. So for nonlinearity, we said that P can be expanded into perturbation series. So this is the linear P that our usual application if the electric field is not strong enough to excite the second and the third order and so on. So when in the linear case, then our P1 is like this. So you know that we have solved our P1. Okay, we have solved our P1. Okay, we have solved this, mentioned about this later. We also have solved our P2. P2, we solve it is 0 because we consider our dielectric is central symmetric, I mean very high symmetry. So we have this